Okay, let's unpack this. Every day, we hear reports about the incredible speed and just the massive scale of large language models and AI development. And the prevailing narrative is pretty clear, isn't it? This relentless acceleration must be translating into huge, measurable productivity gains for all of us.
Right.
But what if that widespread assumption that, technological advancement automatically equals proportional productivity, what if that's largely an illusion? Our sources today suggest we need to look critically at what's really driving LLM progress. Maybe view it less as pure technical advancement and more as something they aptly call hope marketing. So that's our mission for this deep dive. We're going to analyze a really profound historical pattern, specifically how exponentially faster hardware speeds have been used over, say, the last 5 decades. And we'll show how this exact pattern seems to be repeating itself right now in the age of generative AI.
It connects technology to economics and human psychology, which is fascinating. I mean, think about it. If computing power has been expanding exponentially for generations, we're talking chips thousands of times faster than 40 years ago, why hasn't human productivity, universally followed suit? We're connecting the dots here between the historical Moore's law, the famous Asolo paradox from back in the 80s, and this modern, frankly, frustrating issue of software bloat, which you could argue is kind of the inevitable outcome of certain economic incentives. The central question we really have to grapple with is this: are we truly building exponentially faster tools? Or are we maybe just building exponentially more comfortable, more human-friendly interfaces? And crucially, what is the staggering computational cost of that comfort?
Right. So to understand where LLMs fit today, we really have to start with that historical foundation, Moore's law. This was the observation, right, that the density of components, transistors on a chip would roughly double every 2 years or so. And this wasn't just marketing talk, this was real engineering reality.
Hmm.
Empirically, it held true with really high confidence for nearly 5 decades. It was a period of just relentless, exponential hardware growth. Theoretically, the engine of the global economy was getting twice as fast every 24 months. Pretty amazing.
And yet, here's the contradiction that still shapes our world today. The economic data immediately showed this massive discrepancy. This is the Solow paradox, named after the economist Robert Solow back in 1987. Solow noted that all this hardware acceleration, all this massive investment in computational infrastructure, well, it just wasn't yielding the proportional or even really significant increase in human productivity statistics that the economic models predicted. The famous quote, which was derived from data with about 95% confidence, was basically, you can see the computer age everywhere but in the productivity statistics.
Wow, that feels like a fundamental failure of the tool almost. If the engine is growing exponentially, why is the overall speed of the car, let's say, staying roughly the same?
That is the critical question. And it forces us to reconsider what productivity even means in this digital age. I mean, subsequent analysis, notably by Brynjolfsson in the 1990s, showed that it wasn't necessarily that computers couldn't make us more productive. It was more about how the resources, all that extra speed, were being allocated. They weren't spent primarily on improving core computational speed for the user, making the calculations faster. No, they were spent building layers of abstraction interfaces, operating systems, and eventually network infrastructure. All things designed to make the complex process feel easy.
So it's a resource sink.
A huge one. The moment hardware speed accelerated, software developers immediately consumed that headroom. They added features, layers, mostly designed for comfort, maybe convenience, but not raw efficiency.
Okay, so if Solow's observation held true back when we were still using, I don't know, floppy disks and those early clunky graphical interfaces, are we just watching history repeat itself with LLMs today? I mean, now we're talking about models that need entire data centers just to run inference.
Absolutely. I think that's the core argument here. We have to challenge the basic assumption that newer, bigger software inherently produces better outcomes. In fact, when we look at software today, especially these huge LLMs, a lot of the complexity is just required to sort of maintain the status quo to keep things from breaking. Think about the technical reality for these massive models. As LLMs scale up, adding trillions of parameters, they are still software, right? And they start running into these huge problems that actually slow down development. For example, they suffer from phenomena like catastrophic forgetting.
Wait, catastrophic forgetting, that sounds ominous.
It is, computationally speaking. Catastrophic forgetting is when a neural network is trained on a new task or new data, and in doing so, it suddenly completely overrides or degrades its performance on a task it previously mastered. Imagine training a dog to sit perfectly. Then you train it to roll over, and suddenly it completely forgets how to sit. It's a major technical hurdle when you're trying to scale up these large multi-purpose models.
Okay, so that's definitely a bug, or at least something that needs serious managing. What else?
Well, they also suffer from something called negative transfer.
Okay.
This basically means that the knowledge gained from learning task A actually makes it harder or slower for the model to learn task B. It's like the model's internal representation of the world gets cross-contaminated, you could say, and that hinders optimization.
Huh. So the solution can't just be make the model bigger, because the bigger it gets, the more pronounced these fundamental problems might become.
Precisely, and this is where all the software complexity starts piling up. To manage issues like catastrophic forgetting and negative transfer in these massive models, developers have to introduce really sophisticated mechanisms, things like routing.
Routing, what's that?
Routing essentially involves creating a kind of specialized switchboard inside the model. It's a highly complex piece of software itself that has to decide which specific submodel or which set of parameters should handle any given query.
Ah, I
It's
saw.
basically patching the underlying complexity with even more architectural complexity.
So a significant chunk of the LLM's enormous computational requirement isn't even for the core intelligence, it's just to prevent the system from undermining itself. It's a resource drain dedicated to stability, not necessarily better output.
That's the key realization, I think. And this technical patching, this complexity, gets compounded by really powerful external forces,
Yeah.
economic drivers.
Yeah.
We see this core conflict playing out. Economic incentives consistently prioritize, let's say, value-perceived features. The new shiny output, the cool conversational interface, the elements that look impressive and market really well.
The sizzle.
Yeah, the sizzle over the steak. They prioritize that over the tedious, difficult refinement of core functionality that might actually improve efficiency for a dedicated user.
Makes sense from a marketing perspective, I suppose.
It does. And this constant pursuit of perceived innovation over genuine efficiency leads directly to what we all experience daily. Performance degradation and just massive software bloat. And of course, this trend perfectly reinforces the prevailing business model, the rental or subscription model. Because perceived innovation, that hope marketing, sustains profit far more effectively than, say, a one-off technical advancement that might genuinely reduce human effort permanently.
Because if the task gets done too quickly, why would you keep subscribing month after month?
Exactly.
That is a really sharp synthesis. So the entire system is basically incentivized to look fantastic and feel exceptionally easy to use, regardless of the underlying computational inefficiency, the bloat required to achieve that feeling. Which brings us right back to the big historical pattern you mentioned. How hardware speed was consistently redirected, used not to make core tasks measurably faster, but toward reducing cognitive friction, making the machines speak our language.
Yes, and if we track this trend chronologically, we can really see how processing power has been consumed across history. It basically tells the story of how Moore's law enabled the rise of this digital abstraction layer. So phase one, you've got the command line era. This spans roughly the 1960s to the 1980s. Back then, computing power was almost purely dedicated to computation itself. If you wanted to run a program, you had to learn the computer's language, cryptic syntax, commands. The friction was high, definitely, but the resource usage was pretty minimal.
High friction, low abstraction. Got it. Then came the graphical shift.
Right, phase two. The GUI revolution, roughly in the 1980s to the early 2000s. Suddenly, Moore's law made graphical environments, the desktop metaphor, the mouse, icons, commercially viable. This was a massive consumption of newly available computing power, dedicated almost entirely to the human interface layer. It allowed intuition, pointing and clicking, to replace memorized command line syntax.
And you could argue the trade-off was worth it there, at least initially, because it opened computing up to the masses. But it did establish that expectation. The computer should adapt to us, not the other way around.
Exactly. But that expectation required constant feeding, which leads to phase three. The network and mobile phase, running roughly from the 2000s to the 2020s. Here, hardware gains were just completely absorbed by layers of complexity we now totally take for granted. Bloated operating systems, heavy browser engines constantly updating, the ever-present connectivity layers demanding resources. This is really where overall human productivity gains, measured broadly, truly plateaued, because the resulting software bloat just consumed every available bit of performance headroom.
Yeah, we all know that feeling, right? Your new phone has a chip that's, I don't know, thousands of times faster than your desktop from 2005, but somehow opening a simple word processor or, God forbid, a modern widget-heavy web page feels almost equally slow sometimes. Is that the computational cost of accessibility we're talking about?
That's exactly it. The machine is doing so much work behind the scenes just to load the fonts correctly, check the ads, maintain constant connection to various cloud services, render fancy animations. It's all stuff that often has zero bearing on your actual task output, the thing you're trying to achieve. The hardware speeds up, but the software developers use that speed almost like a license to be less efficient, to add more layers.
Which brings us directly to the present day, phase 4. The AI and natural interface phase, starting really in the 2020s. With LLMs and voice prompting, we see the pattern continuing, maybe even accelerating, but at the highest level of abstraction yet. Massive scale and speed are being redirected yet again towards reducing that cognitive friction, making the interface conversational, human-like, highly anticipatory. So we're still prioritizing comfort and this feeling of ease of use over pure, measurable output efficiency for the human user at the keyboard.
Yeah. When you look at these four phases together, the interpretation seems pretty powerful. Faster hardware and now faster AI acceleration. They function less as engines of quantifiable productivity and more as enablers of what you might call human flourishing through abstraction. We are demanding the machine perform an ever-increasing amount of complex, computationally costly translation work just so that we don't have to mentally parse code or complicated command structures.
Okay, so if the machine is doing all that translation, handling all that underlying complexity, where's the trade-off? Is the true cost just the massive energy bill from those data centers?
Well, the energy is part of it, sure, but it's deeper than just energy consumption. Abstraction itself inherently breeds inefficiency. Every new layer we add, from the very first GUI window to a complex voice prompting system that needs trillions of parameters just to correctly parse our ambiguous human intent, it consumes exponential resources, all just to maintain the user's feeling of comfort and simplicity. The core task of the computer, whether it's calculation or text generation or whatever, is now buried under these mountains of software designed primarily to hide the underlying chaos.
So it's the computational expense of maintaining the feeling of simplicity.
Precisely. You could say Moore's law gave us the sheer power needed to create the illusion of simplicity, a world where massive computational scale, inherent inefficiencies like that catastrophic forgetting we talked about, and market-driven bloat are all meticulously hidden behind a perfectly smooth, conversational, maybe even non-threatening human experience. The product we are often buying today, especially with subscriptions, is primarily the feeling of simplicity, not necessarily a measurable productivity multiplier. So, to synthesize our findings from these sources, we've established this pretty clear historical pattern where increases in computational power have primarily been allocated to making technology feel easier and more intuitive to use. And this quest for perfect comfort, for perfect abstraction, it requires exponential resources to maintain, which helps explain why LLM scale has just exploded recently. It takes that much power and complexity to achieve the level of seamless abstraction and conversational flexibility we now expect. And this comes potentially at the cost of measurable jumps in human output efficiency across the whole economy.
So if we follow this trajectory, this historical arc, LLMs might represent the ultimate culmination of Moore's law's psychological impact rather than its purely computational one. The final, ultimate step seems to be making technology feel completely human, totally conversational, utterly comfortable, rather than making humans demonstrably, measurably more productive in their core tasks. So what does that mean for how you, listening right now, should measure the actual success and the enduring value of the digital tools you choose to use every single day? Is the greatest value the comfort and ease, or is it the raw output? Something to think about. Is your fastest, most advanced tool actually making you faster at what you need to do?